Okay, good afternoon and welcome everyone. It's really good to have you with us for this webinar on optimizing heat pumps and focusing on community buildings. Today we're going to hear from Russell Gibb, an experienced heat pump and solar engineer, and also from Dick Jenkins, who's a property convener for Fetteresso Church in Stonehaven, where they've installed heat pumps in two buildings with CARES support. We're also hoping to keep plenty of time for questions at the end and aiming to finish by 3:30 at the latest. So please do drop a note in the chat to let us know what organisation you're representing today, if any. And also to let you know that the slides will be made available after the session, so you don't need to worry about taking notes. You can just listen in. You can put questions in the chat as we go, and we'll pick up on as many of those as we can after the presentations during the Q&A time. And during that time, you can also raise your hand and ask questions in person. I know some folk who are more focused perhaps on the domestic setting have joined us today. You're really welcome, and we hope the session is going to be useful for you. But when it comes to the questions at the end, we'd like to prioritise those that relate to community buildings. So please just bear that in mind. And without further ado, I'll hand over to Russell.
Hello everyone. I hope everyone can see me. There we go. I was a bit stupid today. I start off with a light-hearted note. I swam in the sea that you can see behind me. I'm still feeling a little bit on the chilly side, though, so if I have to blow my nose, I do apologize. So I'm just going to share the presentation with you, and let's just get that going. Okay, so if anyone can't see the presentation, please let me know. So here we are. That's just the intro slide. A little bit about me. I am a seasoned gentleman. I've been doing heat pumps now for coming up to 20 years, and I am a self-confessed heat pump nerd, I must admit. And the stuff that I do at the moment, West Coast Scotland and quite a few of the islands. And in fact, as I progress towards semi-retirement, I'll be actually doing a lot more of the islands and giving up the mainland stuff. So generally, most of my stuff is servicing, repair, maintenance of heat pumps, all kinds, you name it. And I still keep my hand in by doing installations of ground and air source. Oh, why am I not moving? Oh, there we go. So I'm not going to go over these contents. We will cover them as we go along. So difference between use cases. This is really important. And it's important that we choose the right technology, or you have the right technology for the use case. So if we start off with domestic, that's fairly standard. It's quite predictable in that it's generally a permanently occupied single dwelling with multiple rooms, hot water demand, and also generally occupied, certainly in the evenings and nighttime, and sometimes during the day. However, a community hall is really quite different. It's usually run by a board of governors or a committee. It's quite often a large multi-purpose room with small offset rooms for various different purposes, toilets, showers, water consumption. And the use of it can be very different. Occupancy can be different. Target temperatures, for example, the aerobics exercise might want 16, whereas the elderly forum might want 22. And then we have, for example, a church, which could be a single hard-to-heat volume that is only occasionally used. And then, of course, there's offices where you're used during the day to quite a warm temperature. The building regulations are different, so it has to be at 24 degrees, and it's generally unoccupied in the evening. So you can see there's quite a lot of differences. So what kind of technologies do we have to play with? So we have air-to-air, which is known as air conditioning. It's not officially a heat pump, even though it actually is. Air to energy from the air is used to heat up energy in the air. An air source heat pump, which is the prevalent technology nowadays, is energy from the air is used to heat water, which is then put through radiators or underfloor heating. Ground source heat pump, when I started off, this was generally all that we were doing, energy from the ground into water. And water source heat pump, which I've done a few of, quite rare, is you take energy from a body of water. And I know it's not energy as we know it, but it's still high volume, but low grade energy. So what's the best technology? Well, actually, they all are. It depends on the use case. So what is an air source heat pump? It's the one that's the most prevalent at the moment, even though I will be covering other technologies. So in a nutshell, it is low cost. Well, if electricity is low enough, unfortunately, it's not. Capital invested, incentivized by the government to try and get low carbon heating in, because actually with the electricity mix, carbon mix we have with electricity nowadays, it is actually very low carbon and can be the lowest carbon of all. Um, so heat pump generally on an average throughout the year, it's known as a seasonal coefficient of performance. You don't just take the instantaneous coefficient of performance. Even a Lamborghini can get 60 miles to the gallon going down a hill. Then on average, it's about 300% efficient, an air source heat pump. And you can see with the graph that it's much worse in winter when you actually need the heat, and much more efficient in the summer. So how does an air source heat pump work? I'm not going to go into great complex details about how it works, but I use the analogy of if you spray an aerosol can under your armpit, it feels very cold. And that's actually the liquid inside the canister turning to gas, and by doing so absorbs heat. And then you think about pumping up a tire in your bicycle. Sometimes the valve even gets too hot to touch because you're increasing the pressure. And a heat pump, like many different things like fridges, etc., all work on the basic principle of a hermetically sealed closed loop cycle of compression at one point and expansion at the other. One absorbs heat, the other gives it up. And with an air source heat pump, it gives it up into a water body, and with air conditioning, it gives it up to an air coil unit. So heat pump performance varies very vastly, and I apologize if you know this already, but the coefficient of performance drops for a variety of reasons. One is it's colder outside, and the other main reason is the fact that it's producing a higher temperature. The higher the temperature the heat pump produces, the less efficient it is. When we are designing systems, we take into account the sort of average worst case outside air temperature. That's known as DOT, design outside air temperature. West of Scotland is -4. And then we also have to analyze each individual's fabric and ventilation loss, and we have to take that into account. Radiator sizing is incredibly important, and I will get onto that. And then we also have to take into other consideration things like the production of hot water, times that the heat pump's defrosting, and the building reheat time, which is a really important one. And that's where the energy needed to bring a building, a body, a volume up to temperature. So I use an efficiency analogy. I like my analogies. So imagine you've got a helicopter lifting a body of water, and the body represents a bucket of energy. The higher that the helicopter has to lift that bucket of energy, the more energy that's actually consumed. The bucket of what energy is not changing no matter how high it goes. The same applies for heat pumps. The higher you have to lift that energy, the less efficient the system will be. So in an ideal world, we would actually manage to heat our target with as low a flow temperature as possible. And this is where emitter sizing is so important. We have to be able to achieve a high target, a target room temperature without needing any additional heat gains. We're not allowed to consider sun coming in the window, or the fact that it's a kitchen and the oven's on. And we have to make sure that it works down to that selected outside air temperature of -4. When it is very cold, below that design outside air temperature, then there are times when heat pumps need a little bit of extra heating. So we want to do that with as low a flow temperature as possible. So where you may have been used to a gas boiler heating radiators and the radiators were too hot to touch, now we have heat pumps only getting the radiator warm, and you're still needing to heat that room. And so we have to use larger radiators. Now we can do that with physically larger radiators, or maybe triple radiators, or even fan coil units like the kick spaces under the kitchen, or underfloor heating. Now I don't know what technology you have in your building, and I hope it's the right one. But if you've got issues with rooms not heating up, that might be one of the things. The emitters may not have been designed to be big enough. Okay, and oh yes, and a little note. When people say I still want a towel radiator, you still do dry towels with warm towel radiators. It just takes a lot longer. Now, there's another thing that is very important, and that is weather compensation. So, again, air conditioning units don't tend to have it. I don't believe. Correct me if I'm wrong, but certainly air to water, ground to water, etc. heat pumps do. And what they do is they will lower the target temperature of the fluid flowing through the emitter system, depending on whether it's getting warmer outside, and vice versa. If it's very cold outside, it'll use a higher temperature. And you want that weather compensation curve to be as low as possible. And I'll come on to it a bit later about how we can find out whether or not you've got the optimum. Um, so the sophisticated heat pumps you have nowadays, what they also have is a room sensor inside the building. And not only will they use the outside air temperature to decide what temperature of water to produce, but they will also self-regulate and adapt the heat curve, as it's known, so that it's running as efficiently as possible. And I'm going to cover the fact that I'm saying at the bottom here that systems should be left on 24/7. I will get on to that later. So the other thing that we have to take into account is the fact that a heat pump can only do one thing at once. So it can either do the hot water or do the heating, but it can't do both at once. So if you've got a fairly large hot water load, like a 300-litre cylinder, and quite a few people using it, then there'll be quite a lot of the time that the building is not being heated because it's doing the hot water. And we have to take that into consideration. So we may have to size the heat pump to be 125, 130% of the size needed if it was just doing heating alone. So we take that into account. So I use a spinning plates analogy, another little analogy. And you imagine the heat pump is spinning the plates all the time. Heat pumps are just low temperature sources. They don't cope well with bringing large volumes of mass up to temperature. They are sized to perform extremely well, just coping with the fabric and ventilation loss, plus a little bit more. So if you have to bring a building up from maybe 14 degrees to a target temperature of 21 with a heat pump that's been sized, just about right, it will take a very, very long time. So and that's why it's really important not to let the building cool down too much. So I have a Valent air source heat pump for my house, and I've used its timer control for 12 different times, and I have these varying things where it's only changing by 1 degree at any time, just to try and get everything to be gentle and not too much of a shock. So it's important that when you control your heat pump systems, that you keep, for example, the hot water on permanently, even though you can use timers if you've got, for example, economy 10. But just bear in mind that if you've got a very cold hot water tank, it will take quite a while and it will rob you of your heating. And I also recommend you keep the heating on permanently. You don't switch heat pumps off during the heating season. It's fine during summer, but during the heating season, just set it back a little bit, maybe 2, 3 degrees, maybe at night time, 3 degrees, during the day, 2 degrees. And there is evidence that trying to run a heat pump system like a mains gas boiler actually ends up costing a lot more than it should because of these problems of inertia. So my assumptions for you guys is that your system has been designed and installed professionally, that your system is and has been regularly maintained, and that you actually understand the basics of the operation and control of your system. Now, in an ideal world, you'd know someone who really knows how to use the system, a bit of a nerd, and then you have access to someone who can help you and who wants to do so. Really want to be, really into it. Quite often there are, 15-year-olds who love getting into tech. Try and involve them. So controls. Controls is a really difficult subject to cover because there is no single control system that's the same. Every manufacturer comes out with some different way of doing it, some different app, some different controller. And one of my biggest problems is when because I cover every heat pump out there, and when I come across a new heat pump system and having to learn the controls, so I know what it's like for you. Air conditioning tends to be single room sensing. So it'll take, and they tend to have, 4 different modes of operation: heating, cooling, dehumidification, and just simply circulating air. And they tend to be sensing a single temperature in that single room. So there's not an awful lot of controlling going on. And I don't know how good they are when it comes to internet connectivity and remote control. And I don't even know, depending on what air conditioning system you have, how easy it is to be able to retrofit an over the internet controller. And it's something I think we'd have to look at on a case-by-case basis. Room stats are interesting one for air source and ground source heat pumps, in that quite often we're in this country where unfortunately people are very sort of, they stick to their own thing. So the heat pump company comes in and does the heat pump, and the underfloor heating company or radiator company comes in and does their bit. And so quite often you have two autonomous systems. You have the heat pump with its own room thermostat, and then you have each room having its own stat. Now, which one should take preference? What's the priority? And what I recommend people do is, when you're initially setting up your system for, you're trying to optimize it, is that the room stats should be a temperature limiter. So in other words, if they were wide open, set at 30 degrees, you want the heat pump thermostat to be able to get the house or office or community work just the right temperature, maybe slightly above. And then you use the room stats just to limit the temperatures. So for example, if the hottest room in the house you wanted was the living room, you'd limit that to 21, and then limit the bedrooms to whatever, 18, etc. When you use timers, I would be very careful with timers, because timers are quite a bit more abrupt, and they sometimes just literally switch a zone off and then switch it on again. And the problem with that is that if you've got an underfloor heating, for example, in a slab or a screed, it can take hours for the temperature to recover. So you need to be really careful with timers as well. And in an ideal world, like I say at the bottom, internet connectivity would be ideal. So I think what the best thing to do is if you've got a particular controls issue, is maybe raise it as a specific question at the end. So monitoring, reporting, remote access and notifications. As I've said, quite a few heat pumps, especially the modern ones nowadays, have a good app, and the Valent app that I've got on my phone is fantastic. But like with everything else, they're all completely different. But I recommend that, if you don't know how to use the app, or you don't know how to use your controls, I really do recommend that you learn how to do so. Do have a play. You can't break it. There's no harm in trying things, see how you get on. But bear in mind that heat pumps are very slow to respond systems. Now, if you're in a situation where we've got an alarm notification, I'll just cover it here, even though I'm covering it in greater detail later. There are a few things that you can do that you can keep an eye out for. If there's not enough water, this is a heat pump, obviously, if there's not enough water flowing around the system, then what you can quite often get is you get a high pressure alarm on the heat pump. So if you get a high pressure alarm, then try opening up more circuits. I don't know, a hallway, turn it to maximum, and that might solve it once you've reset it. Look at the system pressure. This is unfortunately a very common complaint, is people say, oh, my heat pump stopped working. I can hear air gurgling around it. It might be that the system pressure, and that you can see on the pressure gauge, has dropped to, for example, below half a bar, even quarter of a bar. And what can happen is that when there are automatic air bleed valves in the system, they can end up sucking air back into the system, and it causes all manner of problems. And also, a thing you might be able to do yourself is a filter being blocked. So you might be able to flush that out yourself. Quite a few of them, you just shut a couple of valves and open up the bit at the bottom, and all the rubbish comes out. So the eternal question, optimization. So the term for optimal is the best or most favorable performance. So how do you know that your system is running optimally? Well, I'm afraid the short answer is you don't. And it's actually really hard to ascertain. Most systems don't run optimally, and it is actually really hard to attain. So some questions you might want to ask yourself. Is every room that I'm heating hot enough? If I turn up the stats, how hot do the rooms get? If they get too hot, then your weather compensation curve is not set correctly, and you could reduce that and keep reducing it. Are you often running out of hot water, in which case there may be problems with the hot water? Do you notice the heat pumps stopping and starting a lot? Now, in the old days, we used to have these fixed speed compressors, And what would happen is that you'd see them turning on and off a lot. And if they turned on and off too often, it would kill them. But even with the new modern inverter-driven heat pumps and air conditioning units, if they're stopping and starting too often, it's not good for them. And that means there's something not quite right if they're doing that. Ideally, your heat pump would be running constantly at a very low level, and then it would ramp up and down. Other times, for example, when you're heating spaces that you shouldn't be unoccupied, is there something you could do better? Are immersion heaters being used? So some heat pumps have built-in electric immersion heaters, and you can actually disable them. But the trouble is, when they're enabled in auto mode, what can happen? This is particularly prevalent with NIBE heat pumps, which is why there's so much bad press on the internet about NIBE heat pumps. If you, for example, have got an underfloor heating slab that is cold, or you've let cool down too much, when the heat pump comes on again to heat it back up again, the heat pump senses that it's too far behind. And then what will happen is it will actually then start using electric immersion. And it's amazing, actually, it doesn't even tell you it's doing that. So you could end up having your electricity bill 30% higher than it needs to be just because of this automatic feature. So you need to make sure that you are in control and you understand how your heat pump works and what's going on. And the final question is, have you noticed any gradual decline in the performance of the system over the years? Because certainly underfloor heating can degrade just by, I'll come on to it later about in the what can go wrong section. So my recommendations, basic recommendations, that I've got many more, but these are the important ones. So we've obviously just recently had that really bad storm, and I had a little flurry of activity after it when people were saying, "Oh, my heat pump's gone mental." I would recommend when you know a storm is coming in or there are going to be electrical works or things like that, shut your system down, and you should be able to do it gracefully. You don't just kill the power. Shut the system down gracefully and then isolate it from the mains so it's completely isolated. It generally with storms, we don't tend to have storms when it's below zero, so there shouldn't be any damage to the system. I recommend you have the system regularly serviced and make sure your service engineer records annual data. For example, when I do servicing, I record how many hours it's run for and starts and things like that. You want to be able to compare data. And also in terms of annual servicing, because some people think that, heat pumps don't need service at all, which is actually a load of rubbish. If you've got a hot water cylinder, by law, it should be serviced every year. The G3 regulations mandate that it's tested annually. And it's really to stop your hot water cylinder turning into a bomb. I'm a great believer in monitoring. Monitor, monitor, monitor. And then once you've got data, facts, the facts will then speak for themselves. Do try and read the manual. I know not every manual is written for the consumer and is sometimes written for engineers, but have a good read of the manual and try and understand everything that it's saying, especially things like the weather compensation curve. It's important to know that. Or recruit a geek, as I've said. Don't be afraid to experiment with settings, but if you are going to change settings, do take note of what they are before. I've had to a couple of times perform a factory reset because they fiddled with too much stuff. Do prohibit others from changing anything. So this is really important for community groups and community buildings. Or for example, if you've got a property that you rent out, people will fiddle, guaranteed. And you really need to stop that. Ideally, they would only have control maybe of the individual room stats, but not control of the main controller for the heat pump system. Air conditioning is different. You've really got up and down, and that's kind of it. So that might be okay to let them control that. If you think that your system is non-optimal, then do fix it. It's really important because it will actually pay for itself over time. So here are the particular issues that might affect non-domestic installations, as I've said. So non-domestic installations are absolutely fine until they're not. Failures often come as a shock to a community group with subsequent greater impacts. For example, you have to cancel lessons, everyone's panicking, and then you're trying to scratch around, trying to work out what you've got, etc. Now, quite often, community systems are well engineered, but not necessarily well designed, I hate to say, commissioned or maintained. Ironically, you don't often get what you paid for. And the reason being is that, for example, it might have been some specifier. It went out to tender and some specifier got it. They work in Glasgow. They don't quite often know much about heat pumps, I hate to say, and they will put it out and they'll choose their best buddy. Sorry for being cynical. They'll choose their best buddy company that they've aligned with to put in a system that's not necessarily the right system. And then that company, once they've finished, disappear. They might have given you a pack of information, and they might have actually spoken to you for 10 minutes about your system. And then the other problem is that you may have had a rapid or even a reasonable turnover of caretakers who look after the system, and that knowledge is lost. So it's really important in your scenario to have a decent information pack. I recommend that you get I know you shouldn't say it nowadays, but an idiot's guide to how to use your system and what the basic components are. I think that's really important so that if there is a turnover of people on the community group, that they can learn the knowledge quite rapidly. Community people are just normal people who don't have a lot of spare time. So we can't expect them to be experts, and they need to know who to contact. And that's really difficult because they can't get in touch with the original installer. So who do they contact? And quite often, another thing in community groups, too many cooks, too many people with access. So I've been asked to think about costs. So unfortunately, there's no clear answer to costs. The differences between a domestic and a non-domestic installation are actually surprisingly little. There's generally more of or bigger stuff, but generally it's the same stuff between the two. So again, looking from my viewpoint, an annual domestic service on an island, and that includes all the follow-up notes, including a share of the fixed overheads and the travel and the accommodation and I think overheads like that, ferries, etc. I charge about £210 and I'll be there for a couple of hours. But I've heard of very high fees for less, I'm afraid to say. And materials tend to be extra. So for example, generally, if it's a well-maintained system, materials might only be a tenner, a bit more insulation, a bit of corrosion inhibitor. But if the domestic hot water cylinder expansion vessel has been neglected for a few years, that might be gubbed because the membrane's stuck to the inside of it, because they always fill up with water. So that's another 60 quid here, 6 quid there. So if you're thinking about what to budget for, I think maybe budget, if you're a domestic, to budget for about 250 a year, maybe a year and a half. You don't have to give it a year, even though actually systems that are brand new and within warranty do need to be serviced every year. And that applies to commercial as well. And then commercial groups should maybe budget for about 400 a year, I think. And then air conditioning, I don't think they need serviced. This is my personal viewpoint. I don't know what they need. You can do the filters inside the indoor unit yourself. Just stand on some steps and clean the filters. The outdoor unit you can clean yourself. Just be careful you don't damage the fins. Just take the mold off it, give it a nice wee clean. They really are that easy to service. And you do not need to pay an F-gas registered company to come service it unless there's a problem. Different if there's a problem. So what tends to go wrong? What actually can go wrong? So if you don't service a system, a bit like your car, you've got to expect the fact that it will fail and, it might be a little bit more expensive than, stitch in time. Power surges can damage systems. So like I said, if you know something's happening, shut it down. Insufficient system pressure, I mentioned that before. Blocked filters, pump failures. I still look after a heat pump in Ayrshire that the pump has run for 110,000 hours and it's still running. So they do last, but they do also fail. Fan motor, that's quite a common problem. You might maybe get 5 or 6 years out of a fan motor. Underfloor heating, they have the little actuators on the manifold bar. They have the little actuators on the top, and they also have they're known as return pins. and they're the bits that the actuators push down upon. The actuators can fail and the return pins can jam. So if you have a room in your community hall or in your house that's stopped heating, check the actuator actually opens up. And if it does, unscrew it, remove the actuator, and check that the pin's not jammed. And then you can actually free it off with a little bit of lithium oil or WD-40. I've mentioned hot water expansion vessels. They're the thing I think I have to service more than anything else. Pressure release valves sometimes start to weep, especially if there's been insufficient expansion in the system. They're quite often having to blow off quite often. And automatic air bleed valves are notoriously unreliable. And then finally, the motorized valves if they're the cheap ones, the sort of metal box Honeywell valves, they have a little spinning motor in them that spins virtually constantly, and they only last about 3 or 4 years. And the other thing that is rare but does happen. So if you look at the picture at the bottom right, that's a frozen heat pump. So that literally was completely solidly frozen, and that's a new heat pump. And what happened is the building had been allowed to cool down too much. So when a system is trying to heat up a building that's stone cold, there's not enough heat in the radiators. Say the water temperature is only 6 or 7 degrees. When it does a defrost, it doesn't have any heat to draw from, and therefore it actually can't ever get out of this self-perpetuating frozen situation. And it's nasty. Yeah, you have to use hair dryers and things like that. So what can you do when things go wrong? So I'll do the obvious things that I mentioned before. Check the system pressure, check the stats are working, check the filter isn't blocked. Is everything powered like it should be? For example, if it's underfloor heating, is the manifold controller lit up and running? And then try what I call a hard boot. Gently shut the system down gracefully, remove the power for half an hour, and then switch it all back on again. Does it come back to life? Quite often it does. Think about anything that's changed. Has there been a power surge? Take note of any, because all that information is very useful to an engineer. Take note of any fault codes and error messages that you've been made aware of. You can even take a video and send it by WhatsApp to your friendly engineer. Give any service engineers remote access. Some systems allow you to add another user or service engineer to actually be able to go into your system and monitor it. Now, when you have major problems, in other words, nothing you can do fixes it, quickly engage with an expert, and then they can diagnose remotely. Quite a few times I've actually shipped parts out to Isla, knowing what the problem is, because either I've seen it before or I've managed to diagnose it with someone, me guiding someone on the island, and then a local engineer who doesn't have to be a heat pump expert can change it. Because you'll be pleased to hear that most repairs are relatively simple. In saying that, when air conditioning fails, it tends to be not simple. But most repairs are relatively simple and not that expensive. So here's some installations I've been involved with, some old, some new. We've got some air source, we've got some air conditioning, ground source. I was a bit younger then. Oh, look, I had hair. And, there's not a lot to say. That Valent is the system that I've put in just a couple of weeks ago. So that is my presentation over. Thank you for listening. And I shall then stop sharing if I can remember how to do it. There we go. Thank you.
Thank you very much, Russell. Great to hear from you, and fantastic presentation. Um, if people can hold their questions for now, or do feel free to drop them in the chat, and Russell can take a look at those. But in the meantime, we're going to hand over to Dick Jenkins from Fetteresso Church, Stonehaven, to hear about their experiences. So over to you, Dick.
Hello, actually, it's Dick Jenkins. There is another Duncan in from Stonehaven is dialed in, but I'm Dick Jenkins. We installed two systems over the last couple of years in a church hall in a church building. And as we go through the presentation, I will just go through some overheads just to let you see roughly what we've got. The church hall could be classified as a large games hall, and we installed that with a heating system in there first, And I do have to say that ours is an air conditioning system. It's not an air source heat pump. So the air conditioning system has an external compressor and an internal condenser, which works in the same way as the heat pump, except there's no water system in it. It takes the heat from the external air and it heats the internal air. The we installed the system in the hall, which is a 1970s concrete structure first. And with a winter of operating experience, we had enough confidence to then install a similar system in our church sanctuary. What we've got here is a picture of our hall roof before we started. It gives you an idea of the size of it, and then as we go through this, you'll see that we installed a solar farm on that area. So there's the solar farm. So there's 25 kilowatts of heat there, of power there. The way our system works is completely different from the way that Russell described it, because when we want to heat our space up, we put the heat pumps on, and it heats the space up. For instance, our hall we can heat up in about half an hour. So the users, and there's a variety of users, the users come in and they've got something that's very similar to a television controller, and they start the system up and away it goes. The as After that, after we had done the hall last year in 2024, we installed a similar system in our church sanctuary. The system in the hall was fairly straightforward. It was four heaters. The sanctuary involved four heater systems. So each system actually had two heaters in it. So we had a total of 8 heaters inside and 4 outside. If you keep going through it, so that's the outside compressors for the hall. If you keep going, Isla, that's what the inside of the hall looks like. You can see the condensers on the walls of the hall there. And if you look down at the bottom, if you look down at the bottom, you can just about see the old radiators which were here. If you keep going, Isla, this is the inside of the church sanctuary, which once again you can see the old radiators down in these locations here, and you can get an idea. It's a much larger volume. So this would be the volume, but the equivalent of a large games hall, whereas the hall is a medium games hall. And you can see now, oh, that's the inside of the sanctuary looking from the other direction. Keep going, Isla. We can see here back on the roof of the hall, but you can see these are the compressors for the heat pumps in the church. So this is the church building, which is a 19th century building where we've put a modern air conditioning system inside it, using these external heat compressors. On you go, Isla. And there's what a heater on the inside of the sanctuary looks like. Now, I was asked to talk about the problems. As I said, when we installed the air conditioners in the hall, we installed the air conditioners, we switched them on, and away we went, no problems at all. When we did it in the church, which was this, they were using different models of heat compressors and heaters. So what we found was that the legs which carried the gas joining the external compressors with the internal condensers, the legs were much longer, and we found that it took an awful lot of shuffling around to get the correct volume of gas in the system. So the system didn't work very well to begin with, and it took a fair bit of jiggling around to get it going. and that involved us working with the installer to get there. Um, Going on from there, the control system in the hall is just quite straightforward. As I said, it's just a small device that's similar to what you would use to control your television. The control system in the sanctuary is is a bit more complex, and also it takes about 5 or 6 hours to heat the sanctuary, so that we really need something that we can control remotely or using timers. And what we found is that the control system is really quite complex. And so we had to get the installer to set it up once in a system that we anticipate how it gets used. And then we had to set it up so that it heats the system every night between 5:30 and 7:30. Now, the reason that we did it in that timing is that when you buy electricity, if you buy it during the night, you can buy it for half price. So in the summer, so what we had done is installed a battery system so that in the summer we charge the batteries up from the solar panels, and in the winter we buy the electricity at half price during the night and charge the batteries up, and then we run the system off the batteries during the day. So what we found is that we've actually got quite a complex control system, which it gets used by multiple users in what's basically a community hall. Now, the other problem we have found is in the hall, the heaters are quite high level, and so any noise they produce is quite remote, and it's not really a problem. In the sanctuary, as you can see here, the heaters are at ground level, and they do produce a little bit of noise. Now, if you've got a hearing problem, an old age hearing problem, you won't know that the noise is there. If you've got somebody with tinnitus, they will know everything that's going on in these heaters. But what is part of the control of the heaters is that they can operate either in heating mode, in fan mode, or in air conditioning mode. And what we've found is that we have to turn the heaters, we let the system warm up, then we have to turn the heaters onto the fan mode, and then we have to throttle the fans back so that they don't they minimize the amount of noise that comes out of them during an operational time. So what I'm trying to say is the system I've got here is different from the way that Russell described it, because he described an air conditioning system, or he described a heat pump system. Ours is an air conditioning system, and it's got a more complex mode of operation. It's something that you can get on top of, and what I would say is that our congregation is absolutely delighted with what we've got. And what I would also say is that over the piece, we have managed to half our energy bill costs by running our system the way that we do. I'll hand you back to Isla now so that she can handle any questions.
Thank you, Dick. That's really fantastic to hear, and yeah, great to hear about your installs and what you've learned through that process. So we've had some questions coming in. We're going to stop the recording now if we can.